is Stuart. I work for Columbia Law School. I presented last year here at Cali this project that I'm doing there called Outlaw, which is our free open source Westlaw clone, sort of. I'm not going to talk about that today. Instead, what I'm going to do is try to give a really rapid-fire overview of a lot of the technologies and frameworks that I explored and looked at while I was working on Outlaw, and hopefully some of those are things that you will find useful in developing your own websites. And then Dan from Cornell is going to go into a little more specific stuff, talk about what they've been able to use there, and Elmer's going to show us some live examples of this stuff in action. So, this is what you are probably all very familiar with. This is the standard way of developing dynamic websites for the past, I don't know, however many years. And it has just these four basic components. You're running a physical server running Linux, and it's one server per application. The web server is usually Apache or something that's serving files or pages generated by a script. And you're using a relational database to store your data, and some kind of scripting language like PHP or Perl to generate pages on demand. But in the last 5 years or so, there's been a whole new set of technologies that have shown up and have really kind of just blown the whole field wide open and really changed the way you can develop dynamic sites. These are not necessary. They don't really change anything fundamentally about what web development is, but they offer you a lot more options in how you can design things. So I'm going to go through these one at a time and try to talk about what the principles behind them are and why you might be interested in them. So the first one is the one you're probably most familiar with, and that's virtualization. Now, that's a pretty simple idea. You run some special software on your server combined with some hardware support, and it turns one large server into several smaller ones, each with its own copy of the operating system and its own memory and everything else. Now, you might ask, why would I actually want to do this, turning my expensive server into a bunch of cheaper servers? And the basic answer is it gives you a lot more flexibility in how you can configure things. One of the most popular reasons for virtualization in servers is to make more efficient use of your hardware. So if you need your database server and your HTTP server configured differently with different sets of packages installed, you can do that and still run it on one physical machine. It also makes it a lot easier to test out different configurations. You can start a virtual server, reconfigure it, set a bunch of things up, see if it works, and then if it does, then you move that into your deployment. It's also actually beneficial from a security standpoint because each of these virtual servers, although they're all running on one machine, they can be completely isolated from one another as far as the network is concerned. So even if one machine gets rooted, the others will still be fine, and you can just shut down that machine and start up a new one. So basically, running virtual servers makes it much easier to create and manage new servers as you need them. But where this really gets fun is when you don't own any physical servers at all. And this is where I'm going to talk about cloud computing. Now, a lot of other presentations here at Cali this year have talked about cloud computing mostly in the context of applications or software as a service, where there's some other service like Google Docs or Dropbox, and it's running somewhere else and you're just using it. What we're going to talk about here in this session is cloud infrastructure, where it's your application, your code, running on somebody else's hardware. And the undisputed leader in this field right now is Amazon with their Elastic Compute Cloud service. Now, this is not anything radically new. They've taken what you get from a typical web hosting provider, where you get a virtual server running on some large shared server that they own, and you can configure it to run your website. What Amazon has done is they've abstracted the process out a little bit more. So instead of getting an account and reserving a server for a period of a month, and paying ahead of time, you can actually rent them by the hour. And you can have as many as you want. These are the basic costs. The small instance is 10 cents an hour. So if that's suitable for a moderate use website, web server, and that'll run you about $70 or $80 a month when you add in the bandwidth costs. So that's not much more than you would pay from a shared hosting web server provider. The large and extra large instances just give you more memory, more local disk space, and more processors. There are also what they call high CPU models that give you more processing power relative to the amount of RAM. And again, they charge just a little bit more. But in general, it's very cheap. And because you can start and stop these whenever you want, you really only pay for exactly as much as you need. There's a lot of terminology associated with EC2. This is some of the basics. You have an instance, which is one running virtual machine, and you can launch an instance using an image as the starting point. An image is just that. It's an image of the root file system for that server. And they have dozens and dozens of images with different Linux distributions pre-installed. Some of them are even pre-configured for a particular type of application, like a database server or a web server. And then you can also create your own customized images that have all the software you want pre-installed. One of the things that is sometimes a little bit challenging with running these is that although there is a local hard disk, it's a virtual disk, but it's still a hard disk associated with each image, it's not permanent. When you shut down the image, all that storage disappears and you cannot recover it. So to work around that, they created these elastic block stores, which is sort of like having an external hard drive that can be plugged into any given instance. And so you can create one of these virtual disks any size from about 1 gigabyte up to 1 terabyte. And it's persistent, it's always there, and then you can attach it to any running instance and actually just mount it as an ordinary block device in Linux. You can also get Windows images and Windows instances. It's slightly more expensive, and you have to deal with the licensing for Windows Server, but you can do it. Then there are the availability zones, which you don't really need to worry about at first. Basically, that's a way for Amazon to describe the different data centers that they're running these actual physical machines in. They won't tell you where they actually are, but they will promise that the different availability zones for each, as they're labeled, that those are in different physical locations. So, this is probably not a big deal for us, but if you really want to build a service that is disaster resilient, then you can run instances in multiple availability zones, and you know that they're running in different locations. The elastic IPs are a really cool feature, actually. When you start an instance in Amazon's cloud, you get a public IP address assigned to that instance. But you can't predict, you don't know what that IP address is going to be until you've started it. So what you get with an elastic IP is basically just a static IP address that you can hang on to, and then you can assign it to any instance you want. So this is really, really useful, actually, for deploying new versions. So what I do, when I'm about to deploy a new version of the code that runs Outlaw, I start up a new instance with the new code running, and I test it out, make sure everything's working, and then when I'm satisfied that it's ready, I just flip the elastic IP to point to the new instance, and I shut down the old instance. So what I get then is I get a perfectly seamless deployment from one version to another, and there's absolutely no visible downtime from the point of view of someone using the site. Amazon also just recently introduced a new service called Elastic Load Balancing, which basically extends that idea one step further, so that instead of running a load balancer on one of your instances, they will just do that on their network, and you pay a small fee, but it's cheaper than running your own instance. And I think that's tied into the other services. So this is one way you could, this is sort of a typical template for how services might be deployed on Amazon's infrastructure. You'd have an elastic IP sitting in front of one instance running as a load balancer. Now you can replace that with Amazon's elastic balancing service. Then you'd have several instances, maybe small or medium instances, running as your application servers. Those are your web servers. And those could talk to a collection of database servers, which might be medium or larger instances. And the actual data for the database would be stored on these Ebs volumes the elastic block volumes, so that you can keep a persistent store of the data in your database. I've been to a bunch of presentations from people at Amazon, and they've talked about the type of services they were trying to create. And they keep coming back to this concept of scalability, which is kind of a buzzword, but the way the Amazon people use it, I think, is really smart. They say scalability means being able to tailor the exact amount of resources allocated to a given application in real time, subject to the demand that you get for that application. So they say what they're aiming for are services you can scale in 4 directions: up, down, in, and out. And that means scaling up means running the same application on a bigger machine, more memory, more processors. Scaling down is a smaller machine. Then scaling out means adding more machines to a single application, and scaling in means fewer machines. Now, the reason this is useful is that there are a lot of times where you have a service that gets a lot of traffic, a lot of demand, during a very short period. I mean, I think the perfect example for academia would be a registration system or a grading system, where it's getting a lot of use in a very small period of time, a couple of weeks, and then the rest of the year it's not doing much at all. So if you were running this a service like that on a single physical server, that server would have to be big enough to handle the peak demand, and the rest of the year it would basically be sitting there idle, wasting electricity and wasting money. So with a scalable service, if you can design in this infrastructure, you can run a service that always has as much capacity as it needs, and you're not paying more than you need. Now, some people may be concerned by the fact that you don't own the hardware, that you can't control the data center, you can't actually control the physical location of your data. And the best answer I can give to that is Amazon's probably going to do a better job of it than you are. They have huge data centers with multiple redundant internet connections, private, backup power supplies, 24-hour security, and you can't compete with that. They're going to do better. These services do have availability problems. They do go down occasionally, but it's very rare that everything goes down. So if one availability zone has a problem, the other availability zones will still be running fine, and you can just switch your application to one of the others. So really, if you're careful in how you do your configuration and your deployment, you can achieve almost zero downtime using these kinds of services. So that's all I'm going to talk about that. The next thing I want to talk about are these. This is a very broad generalization I'm making about non-relational databases, and I'm calling them document databases. Some of them are actually what you might call column-oriented databases, like Google's Big Table. But generally, they all have certain things in common, and that's all I'm going to try to cover today. The two I'm going to talk about mostly are CouchDB and Amazon SimpleDB. CouchDB is an open source project. You can download it and run it on your servers. It's designed to be a scalable, distributed database system, so it will run efficiently across multiple machines. Amazon SimpleDB is interesting because it's actually a service. It's not something you run. It's a service, it's running, it's always out there on Amazon's infrastructure, and you just use it through a very simple API. And I don't want to go into too much detail about how these work, but I'll talk about just some of the general features that these types of databases have. It's a very different paradigm from relational SQL databases. It's probably the most radical change in terms of just doing things in a completely different way. So in a relational database, you have rows in tables with a fixed schema, and each value in a row is an isolated atomic value. It can't be a set or a list or anything like that. Document-oriented databases are usually storing a document model that's just a set of named fields and values for those fields. There is no schema. You can assign, give a value for any field, whatever you want to name it, and they're all going to be stored effectively in one giant table. So there's just one namespace. And if you want to differentiate between different types of records, you would just add another field that said, this is this type of record. Likewise, because there's only effectively one table, you're not going to do any joins. People sometimes ask with these databases, they ask, how do I do a join? And the answer is basically you don't. You format your data in the records so that you don't need to do joins. And the way you usually do that is through denormalization. And that just means essentially storing duplicate data. And you have to allow for that. That's sort of one of the strict constraints of the relational model that you have to be willing to let go of if you're going to use one of these document models. And I'll talk in a second about why you might want to do that. CouchDB implements something they call maps, which is basically like a view in a conventional database where you write a function and that function is just applied across every record in the database. And whatever the results of that function are, that becomes a new structure in the database that you can then query and create more views on. The reason all these things came out is that people found it was really, really hard to do relational databases in a distributed system. It's almost impossible to efficiently do relational style transactions and consistency guarantees when you have a system that's running across multiple machines. And they've been working on it for years. Basically, just no one's come up with a good way to do it. So Dan Pritchett from eBay wrote this article about how these design constraints were changing. And basically what people found is that to build distributed databases, they had to relax the constraints. And they had to kind of change the way we think about database integrity. So a relational database, you're used to seeing these. This is the guarantees that a relational database gives you. That every transaction is atomic, it's isolated, that every client using the database always has an absolutely consistent state with every other client, and that all the changes will be saved immediately. A distributed database or a document-oriented database doesn't give you that. So instead of ACID, you have base. Kind of a silly pun, but there you go. And what that means, it's several things. Basically available means that the system is resilient to failure. So it's designed to be run across multiple machines, and if one of those machines goes down, the rest of the system keeps working. You may temporarily lose access to the data that was on that machine until it's brought up again, or until a copy of it is brought up again, but the system as a whole keeps on chugging. The soft state, I don't really know what that means, but scalable just means that these systems are designed to scale in a linear fashion. So in order to handle either more data or more users, you don't have to add bigger hardware. You just have to add more machines. And you get linear performance increases as you add more machines. So that makes it much easier to start small, running on a single machine, and then as your needs expand, you can expand the database along with it and not really have to worry about scaling issues. But the biggest and the most important thing on this list is this idea of eventual consistency. And this is really where you're changing the definition of what a database is supposed to do. Eventual consistency just means that what you see from the database will eventually be consistent with all the records and will eventually be consistent among all the nodes in that database. So essentially that means that all of the changes to the database are getting put in a queue, and they will be executed soon, but they won't necessarily be executed before your transaction finishes. So what this means from the client point of view, if you write a value into the database and then immediately read it again in the same program, you might not see your updated value. But it turns out in most web-based applications, that's okay. It's not really that big a deal. And these are computers we're talking about here, so eventually usually means a couple of seconds. That's what they mean. It's not like an hour later. It's a few seconds for it to propagate to all the nodes in the network that are running the distributed database. The next big thing I want to talk about, this is more of a concept than a particular framework, this idea of representational state transfer. It's another buzzword. A lot of people are talking about it and using it in places that it doesn't really fit. But the basic idea is to go back to the idea of the way the web was originally designed. And REST was described in a PhD thesis by Roy Fielding, who was actually one of the guys who wrote the original HTTP specification. So his idea works like this. Everything in the world is a resource, but a resource is not a web page. A resource is some abstract entity that you want to refer to, some piece of information. It could be a web page, it could be a file, or it could be the weather in Denver 5 minutes ago. Doesn't matter. It's something that you want to refer to with a URI, and you can give that URI to people and they can use it to link to that resource. When they actually retrieve that resource, what they're getting is a representation. And there might be many different representations for the same resource. There might be one in HTML, one in plain text, one in XML. And the point is, that's all the same resource. They're just different representations. And HTTP is actually designed to handle things this way. But conventionally, a lot of web frameworks were not. So this is where things sort of change in these different styles of development. The traditional web development is all about trying to recover state in your interaction with some client, like a web browser. So you use cookies, you use session variables, hidden form variables, all these things trying to hide the fact that every HTTP request to the server is basically stateless. You don't know what was going on in the context of what the user was trying to do. So the REST paradigm really embraces that statelessness and says, you can actually design services that work that way, that don't have to fight around that constraint. And the advantage when you do that is a lot of scalability stuff becomes much easier. If you have a stateless system, then you can duplicate that system across a bunch of machines, and it doesn't matter which machine gets a particular request, because every request is the same. There's no information that needs to be stored on the server about what the client was doing. So you can build websites this way. It does actually work. You have to be a little cleverer about how you design your forms and such, but it does work. But where this is really more interesting is in this field of web services, which are basically a way of abstracting some computational service. It might be a database, or it might be a processing server or a storage system, but to present an API to that service that runs entirely as HTTP requests. And what that means is it turns out once you've done that, it's really easy to do client libraries in any language. And you don't have to worry about, remote procedure calls or wire protocols or some binary mumbo jumbo, like if you were talking to a traditional database. In fact, several of the document databases that I showed you, they all use HTTP as their API. They just run a web server and you send requests to that HTTP server, and that's how you interact with it. And this is how really big sites do their data management. I've heard, again, presentations from Amazon, and they say when you hit a page on Amazon.com, what's happening is that the web server you're talking to will send out requests to 100 or even 200 different web services, all running inside Amazon's infrastructure. And those web services each return one little piece of data that's going to go into making up that whole page that you see. So when you think about it, there's a lot of information on a single page from Amazon. There's recommendations and what you've been viewing lately. All of that stuff is being retrieved and stored in some kind of web service. And again, as I mentioned before, there can be different representations for the same resource. And the basic idea is that you have one URI that identifies the resource, the piece of information. And then, depending on the headers sent in the HTTP request, in the accept header of the HTTP request, you can specify different content types, and the server will return whatever type of content you want. There are several frameworks that are purporting to implement REST as a web framework. Ruby on Rails was really one of the first that got into that, and they've gotten a lot of attention for that. I actually think Ruby on Rails is not the best implementation of this system, because it started in the traditional forms and cookies sort of web development, and then a lot of the REST features were added on later. So it's not really a pure implementation. Django is very similar to Rails. It's written in Python. I don't know a whole lot about it, but I know that it's quite similar. Really, I think the most interesting, although it's not very well known, is a framework called RESTlet. And this is actually, it's a really clever idea. They took all of the terminology and the key ideas from Fielding's REST thesis, and they implemented them as Java classes. So this results in some interesting facts, like all of the classes in RESTlet implement the same API. There's only one API for all of the classes, and it's the HTTP API. Request, response, that's all it needs. And because they all have the same API, you can compose these RESTlets and nest them, and use one as a filter in front of the other, and do all kinds of crazy stuff. It's a lot of fun. Unfortunately, it's written in Java, so you have to use Java code to implement it. If you want to learn more about this, I highly recommend this book. I'm plugging it because it's written by a friend of mine, Leonard Richardson, and he wrote this book. Most of the examples in RESTful web services are from Rails, but he also talks about these other two frameworks. The last thing I want to mention, which this is kind of a minor issue, but when you're using a large web framework, usually what happens is instead of the web server, the HTTP server, instead of that being the central point of control for all your applications, instead it's really just a front end. And it usually goes under the name of a web proxy. And basically this means that you have some application running, and it might be in Ruby, it might be in Python, it might be in Java, that has its own internal web server. And then you have another web server sitting in front of that that's doing things like filtering requests so you don't get too many at once in a denial of service attack. It might be serving static files like images and CSS. But then for all the other requests, it's just going to forward that request to your application over a socket. Apache is actually a pretty good proxy. It's certainly not the fastest. In fact, it's one of the slowest, but it's very reliable. It's very robust. And that's certainly convenient if you're doing other things and you've already configured Apache to do what you want it to do. A very popular one that's a pure proxy, it doesn't have any web server features at all, is HA proxy. And a lot of people use that as a load balancer, especially on Amazon EC2. You can run an instance running HA proxy, and it will distribute all of the HTTP requests to a bunch of different application servers. Light HTTPD, or I think Lighty as it's usually pronounced, is similar to Apache in terms of the scope and the features it offers. It's much newer. Some people will claim it's faster than Apache. It's probably a little faster. But it offers a lot of the same options. So if you want to configure CGI scripts or PHP or something like that, you can also do it with Lighty. Mongrel is a web server that's designed specifically to work with Ruby on Rails. It's pretty much the standard web server to use with Rails. Nginx is kind of an interesting project. It was originally developed by Russian spammers, and it is now an open source project, but it is generally agreed to be the fastest web server in the world. So if there are actually a number of sites that are processing very high loads, and they use Nginx because nothing else is faster for just getting the requests put through as quickly as possible. But it's kind of cryptic to configure. It's probably more low level than you want to go. So that's basically it. There are these four big ideas that you can scale everything on demand to meet the needs of your application. You can use a distributed database so that you're not limited to the single machine constraint that you usually get with a relational database. You're using a proxy for load balancing and management, and that proxy is sitting in front of some kind of web service. And again, you don't have to take all of these at once. These are different ideas. I'm just trying to throw as many things out there as possible, and you can explore them and find some that are helpful in your experience. So I guess I'll answer questions quickly, and then we'll switch over to Dan. Anyone? Okay.
That was a bit premature. That's all I did. All right, there we go. Okay, so Stuart already told you who I am. I'm Dan Nagy. I'm the systems administrator for the Legal Information Institute at the at Cornell's Law School. And to give you a practical example of some of the stuff that Stuart talked about, let me get past these because we know where we are. We know who I am. Where we at the LI are right now is on a Linux virtual server kind of cluster. So what we have is your typical cluster. We have a kind of a load balancer up front. Does a round robin between two backend nodes, backend database hooked into all that. We have our factory server hooked in. We have a development server hooked in. We've got a staging server hooked in. And so what we basically have right now is we're not really using a CMS for any of the big stuff. We do have one collection out that we are using a CMS for now. It's topics.law.cornell.edu. You can go look at it and see it's pretty. So what we have is a bunch of hardware sitting in the back room, and our back room is, I don't know, it's probably 3 feet wide. It's about the size of the size of the U-bomber's cabin, right? It's really tiny. Yeah,
That's a lot.
that's where we got it from. But Tom makes me sit back there sometimes, so I'm bad. Thanks. But where we want to be actually is on a relatively more easily scalable utility computing infrastructure, mainly so that we can we don't have to go back to the well every 4 years or so and ask for $22,000 to rebuild with the newest, brightest, shiniest hardware, so that we can keep up with the load that we're getting and innovate. So how do we get there? Well, the way we get there is easy. We just rip out everything we have, rework the entire architecture, shove it into a CMS, and tank most of our hardware servers and stick them out into the Amazon cloud, right? Easy. It'd be like, it's going to be done like next week. So the first thing we did is, and the editor and I, and probably Tom was talking about it long before I came along with Sarah, was moving some of the collections to a CMS. And for a couple years there, we didn't really have a good choice for any content management systems. But recently, and I'm not going to beat a dead horse here because we all know about Drupal. So we had decided to use Drupal to host a lot of our services. And what that was going to give to us was the ability to add and remove features relatively easy. If you think about looking at a web page, this little sidebars you have or the headers you have, that we could add search features. You want to find a lawyer, put a little box up into the Justy Lawyer directory. I don't know, whack-a-mole, something on the side, whatever. Whatever adds value to the site, and gets people to look at it. It also makes it a little bit easier to centralize the look and feel. So when we do things like, we're in a fundraising cycle. So if we add, the give us money header, which you should go and give us money. So when we had the give us money header, it's easier to do across the whole site. It wasn't difficult before, but it's even easier now. And the other thing we can do as far as content, which we're probably going to wind up doing when we move to the new architecture, is something called lazy instantiation, so that the resource is not actually, well, it's there, but it doesn't exist in any cohesive form until you actually make the request for it. So if you're going to go to, it's tax time, you can go look up Title 26 US Code. That exists in Potentia until you request it, and then it exists for real. So that's what we're doing. That's why we decided to go to. Some of the reasons we decided to go to Drupal. The other is because we're doing a lot of outside collaboration. We're trying to do outside collaboration with some other folks. So it allows us, using modules, to wire an OAuth, which is a way that we can use other people's authentication directories to say, oh, you're allowed to come do this stuff on our site. So if we're talking about letting lawyers edit wiki entries for certain parts of law, as long as we can verify that they're a lawyer, and Justy has done a great job of vetting a good directory for that. If they're in the Justy directory, we're going to probably let them edit something. Content updating is made easier, again, for obvious reasons. It's a lot easier to just generate the stuff factory-wise, stick into a database, pull it back out, and display and show it to the user using using Drupal than as anything else. And we can also do hosted collection should we decide to. So if somebody says we have something that's worthwhile to put up, we can put it up and then we can let them independently edit it, should they need to. And then obviously with Drupal, I'm not preaching the choir, I'm sure. There's the centralized backend for data stores. So you would have, most of it you wire into MySQL database typically. You can also you don't have to just use MySQL to get the data in and out. You can use other disparate sources of a centralized data store to get stuff in and out of it. And one of the nice things for us, and one of the things that, I'm sure we have a lot of Achilles heels, but one of the big ones is is release engineering. I mean, we'll sit on stuff forever, but having stuff in Drupal makes it a little bit easier to prototype, look at, and then move from production to development to a production environment. So we're going to go with Drupal, and so the backroom to Drupal has several different parts to it. One of the things that we started playing around with recently is Exist. Exist is an XML database. We've had luck getting stuff out of Exist and into Drupal, and Tom is doing most of that stuff. A lot of the outside data that we get verifies clean as XML, or relatively easily can be turned into XML. And it turns out to be a pretty good way to get stuff that we have, stuff that's coming from outside resources, stuff we get from GPL stuff. It comes in relatively as clean XML stuff that will validate XML. And then the other thing, is MySQL and then Sphinx, which we'll talk about in a second. Again, I'm not going to go into what MySQL is. We all know what a relational database is. But MySQL is the traditional backend for Drupal, and we're having it as such. It's going to wind up being a master-slave kind of relationship thing. So despite the fact that you're not supposed to hack core, we got to kind of hack Drupal's core to make that work for us. And then, again, we got turned on to this by the Justia folks. Sphinx. When we rework the site, we're also going to switch away from the venerable old squishy site search to something a little bit more modern. And so Sphinx looks like it, and actually Sphinx is actually a pretty cool program. It'll do full text indexes, and it actually runs as a daemon in the background. You can actually compile it into MySQL if you want, and if you're running it as a daemon in the background, you can actually attach to it just like you would MySQL and run SQL queries against it, and get quite a bit out of it for that. And then if you combine those two things, like I said, that's where we get our full site text or site-wide text search. The other thing to talk about really briefly, because this is really geeky stuff, is a Subversion Repository, a versioning management system. We're using it now. It becomes more important as we start distributing stuff. And this is for the programmers we have. We're really not going to keep any, because Drupal already does versioning. So we're not going to keep any kind of content in it. But it's mainly so that our code guys have some place to stick their stuff. They tend not to work on the same stuff, but occasionally they will be, and it's nice to be able to collaborate like that. They're very, very in tune with the idea that they need to know where they've been, so they can know where they're going. So keeping multiple versions is important to them. And we're probably also going to bend it, or I'm going to bend it, to managing my conf files, because I got enough of them, and I would like to have a centralized location so that I know that my MySQL conf file I can access that easily, and all different versions of it on my factory server is different from the one on my development server. So we're going to use SVN to manage that stuff. That's enough SVN. And then the other thing we've got running on the back end, and this is kind of interesting, is write scale. And this kind of meshes into the next talking point down the line there. And what write scale actually is it's a third-party EC2 management tool for the Amazon cloud. And before Amazon started building out the services it has, EC2 was a way to get some of the stuff Amazon didn't offer, so like load balancing. RightScale's been doing for a while now. Amazon's now bringing on their own load balancing scheme. What RightScale does is actually make you can get the images as Stuart talked about, which is the non-running instance. It's like an instance descriptor, and you would then RightScale has their own. you would go get a RightScale instance, start it running in the cloud, and then RightScale has proprietary scripts that they have. So you would have a base image, and then as soon as that instance came up, those scripts would automatically configure that instance to be whatever you wanted it to. So it could be an application server, it could be a database server, whatever else you would need, whatever you need it to be. The RightScale scripts can be customized to have it do that. So Amazon is bringing its own load balancing online. I really haven't looked at it much yet, but it should do just fine. There's no reason it wouldn't. The thing that RightScale does get you again is the script, so that you can have one baseline image and then apply the scripts to it to build whatever you need to in close to real time.
And commercial support, right?
And commercial support, if you pay for it. We were talking about this, and I don't know how far this deal extends, but yeah, they do offer a discount to .edge. It's still pretty pricey. The startup fee for .edge is $1,500, $400 a month. So it can be pricey. Although they said that they would just flip our account on for free, but then we don't get to talk to them about anything. We don't really get any support. We just get their proprietary scripts, and we're kind of on our own. So we may do that for now, or we may just see what we can do with just the stuff that Amazon has, because Amazon is building stuff out really, really quick. And that brings us to the Amazon cloud itself. And Stuart was saying the same stuff Stuart said. For us, what's really important is that it be scalable and it be flexible. I mean, that is super important to us. So right now, what we have is a relatively rigid load balancing system. All HTTP requests come into the top end of the cluster, and it's then distributed just round robin between two machines, which are in virtual parity under it. The problem is even, and it was great when I built it 4 years ago, and it worked great, and we never had any load issues. And now we're starting to see the load on those creep up as we get more and more and more hits on the site. And in order to scale that, I then have to I could simply just add another node, but then it's out of parity with the other nodes, and I still have aging hardware. So what this allows me to do with the Amazon cloud is, as soon as some trigger is tripped, it could be load, it could be the amount of requests, it could be the amount of queries being done to the database, I can spin up an extra resource in virtual real time to take care of that. And as soon as the load abates, that resource will go away. So if I needed an extra server to serve HTML, I need another Drupal server up, it would just simply shoot one of those up into the cloud, incorporate it into the load balancing scheme, and start serving hits. So if we get a big Supreme Court case that came down, it would automatically scale to that, and then as soon as that abated, it would go away. It allows us to change the architecture relatively easy if we should need to. So I can move around the way we do factory processing, the way we do development. I see no reason I would change that, but we might. And it also allows us to prototype easier with one-off projects. So if we have we just want to try something to see if it'll work, we have a new piece of technology we want to work with, we get a different kind of database, whatever, we can build something out, look at it. If we don't like it, we can tear it out. And I don't have to have servers standing there dark. I don't have to have physical servers standing there dark that I then would only use once or twice. If Peter decides to teach, do distance learning and stuff, it's certainly going to go out to the cloud. That's something that will sit separate from our production environment. And again, when Peter's done teaching his class in distance learning, that instance just goes away until he needs it again. You're not actually paying for it. The other thing, Stuart had the slide up about the cost for Amazon. Right now it's a toss-up. You see people talking about what the cloud would cost you versus what buying actual physical hardware would cost you. And the one thing, what was an easy sell for us, and Tom actually talks to the money people, I don't, is that it's a predictive cost. You can kind of figure out what it's going to cost you from month to month. So instead of having to go back to the well every 4 years and make a large request for money, you're making a small request, but you're making it on a monthly basis. And then you can kind of chart your progress on how it's going, refine it, so the next budget year you know what to make the request for. But it makes it a lot easier on the money people when they know what the cost is going to be. So you're not going back every few years trying to upgrade some old hardware. And you're never on an old box. I mean, the specs that Stuart showed you for what the instances look like, small, medium, large, those have actually changed over time. So what a small instance is now wasn't what a small instance was a year and a half ago. I mean, they constantly upgrade them, and that's pretty seamless to you. And the price doesn't really go up. The price is only going down for their stuff. And again, we have the predictive cost and the user prototype. And then the other thing it gets us is, you know, after, I know years and years and years ago, there's a lot of, years and years ago, I mean, there's a lot of buzz about the whole Katrina thing and how do we offsite our data. Well, in the Amazon, it's already offsited for you. There's actually no reason you can't keep a physical box on site, just so you have the warm fuzzy of having, owning your data still. And I'm certainly going to do that. I mean, you know, the world could crumble tomorrow, but damn, I'm going to have money. Doesn't matter. So you have the automatic offsiting the data if you stick it on the Amazon cloud. And like Stuart was saying, I mean, you know, it's the I mean, we started tons of instances. We got this little bitty server on that. It's claustrophobic to be in. And Amazon does it so much better than we ever would. And then you can also keep, even within the Amazon cloud, you can keep it in disparate locations because you have East Coast 1A, 1B, 1C. So you can stick it in different data centers. You don't really know where they are, but I would make a guess that East Coast 1A is different from East Coast 1B.
You can guarantee that, actually.
Yeah. Now, the caveat to that is when Sue was talking about the electronic block store, and this is just because I forget this all the time too, when you create the EBS, you have to create it in the same locality. You can't create a different locality and attach it. So you can't have a block store sitting in one zone and attached to it sitting in another. They have to be in the same zone. I learned that the hard way. And there's multiple storage options for it. You have like 3 with Amazon, right? You have what I consider to be cold storage, which is S3, which is where you stick your images when you're not running them as instances. It's also where you would stick a lot of your backups and stuff if you're doing it. You have your elastic block store, which is relatively stable. Think of it as an attached disk drive, an external hard disk. And then you actually get, I think it's like, is it 160 gig? Nick, is it 160? What's the standard small space on a?
It's 160 on the small.
160 on the small, yeah. So even on the smallest instance possible, you know, you get 160 gigs. Now that's volatile. It goes away as soon as you shut the image down. But I mean, if you're using stuff like RightScale, you can move all your data right onto that instance if you want to, and not even have to mount an EBS block store. So, good. That's all I had. Elmer's got what? 12 minutes.
107 slides.
Really? That's up from the 2 you had this morning.
Which is 2 more than you normally have.
Oh, I guess you can ask questions now or ask them after. I'm sure.
Sure. Hey everybody. Here we are. Hello. Let's see here. Right, so here we are at the end of day 2, right? You know, after this, there's only 10 possible sessions to go to tomorrow. So, yeah, I know. And then, of course, the closing plenary where they'll be giving out the door prizes, or the raffle prizes, rather. And you certainly don't want to miss that. And here's a tip for all you Mac users out there. Do be careful not to jam these things in the wrong spot. One time I inadvertently stuffed my power cable into the FireWire 800 thing. It was a cool arc, and it just, seriously, and it just went, it did that. Well, yeah, it just died, and so it was kind of, pretty scary. Okay, so here's what we're going to do, and this is a warning for all you Twitter folks, or Skype folks, rather. Your chats are going to turn up on the top of the screen, okay?
That's not
I'm leaving them there on purpose. So just, you know, watch out. So, what I want to actually do, see now they're going to try it out and see.
You're never going to get anything done.
Yeah, I know, that's a bad idea. So what we're going to do is, how about we just jump right in and launch one of these things, huh? Which is what we're going to do. You need 2 things
to launch an Amazon. That's right. You need a key and a code, or maybe 2 keys. Depends. No, you need an Amazon account, which I think everybody has, and a credit card that doesn't charge your own personal bank account. And that's actually like kind of a sticking point for institutional use.
Yes.
They don't accept purchase orders. They don't do billing. They just charge your credit card at the beginning of every month. So you have to have like a purchase card or something. And if you don't have one, you can go and find the person in your law school who does, because there is somebody. And then you might have to like take them a cake, maybe wash their car, whatever. Get that number, and then attach it to your Amazon account and start running up EC2 bills on it.
By the way, I tried doing that for about 6 months at Columbia, got nowhere.
Yeah. So when you dive in, as you can see, there's a whole map. Like what you do is you start machine instances, which are essentially just like a canned version of your operating system. Used to be just Linux. However, as you'll note, people kept saying, well, what about Windows? And so there, you can actually fire up Windows servers. I've never done it. We're not going to start now. But people do use it. And actually, I was looking at it for the possibility of doing video, because I still like the Microsoft Media Encoder is the best way to like do video over the internet, because the Flash stuff's a little choppy. But turns out Microsoft doesn't support that anymore, only Silverlight, which is worse than Flash. So anyway, you can fire up one of these. You can go and find some stuff that other people have already loaded up. There we go. So there are currently 2,299. Although interestingly enough, when I looked before, there were 2,300. So one's been removed. So you can add and remove them. And if you're looking for like something special, because you can see there's like lots of different versions of Linux and Windows and stuff. But say you're interested in trying out the Asterisk open source PBX. Oh. The open source PBX. So you can do a search and you'll see that you could actually like launch your own PBX and fire up your own VoIP operation with just the flick of a switch. But what I've done, I've actually created one of my own. Because that's one of the things I like to do. What I did was, I basically wanted an image that I could use over and over again as sort of a baseline for all of the web stuff that I was planning on doing. So I put one together and I saved it. It's about takes several hours. Allot yourself a day to do it. So that, because you've got to basically set up a Linux server, get all the software you want on it, get it configured the way you want it, make sure you've got all of your startup services going and all that sort of stuff, and then make the image, which is a whole series of steps, and then and then test it, and then when you messed it up, then you gotta throw it away and start over. But eventually you get it right. And we'll select the prototype. Now you can start a mess of them. So if you need to scale up real fast, and you've got the prototype that you want, you can start like 25 or 30 of them at once. Important to know, the charges on your card begin accumulating immediately. So don't say, hey, let's see what happens if I fire up 100, because it'll fire up 100 and then charge you for them. So, and you pay by the hour for running these.
Partial hours.
Actually, it'll only do 20 until you
Oh,
ask
I do
for a larger
20.
account.
Oh, okay. What do I know? I've never tried. But we're gonna do just one. It's a 32-bit. We're gonna stick with small. You create key pairs, which I'm not gonna get into because frankly it usually gives me a headache. Hello? That could have been me. Let's see. I will pick the Kali AWS. You can set your security groups. The security groups are kind of like firewall settings. Somebody's phone. I know, I think somebody's messing with it. The security groups are like, they're sort of like firewall kinds of things, so it tells you what ports are open and closed and that sort of stuff. So, because normally when you fire one up, the only thing that's open is SSH. So you can immediately get in, and but then you can set these profiles.
It's different from a host-based firewall. There's a host-based firewall in
Yes.
instance, and this is kind of like your network-based firewall.
Yeah, this is like a network-based firewall. Yes, thanks. Right, because you can do this for like as you can see, I have several different ones here, and we're actually going to go with Kali, and whoops, wrong. It's this silly Mac operating system. Okay, and as you go along here, you can actually create these things if you need them. And then we'll hit launch. Now this is going to go and be loading off. So it will take a few minutes, and we can actually cancel that. And we can go over to the instances. Now that's my phone.
Didn't jump off you.
This is actually John. Yeah. Anyway, so I should probably, well, my radio didn't go off. That's how you're supposed to get a hold of me if it's official conference building or official conference business. So I've already got 2 instances running. The third one's starting up, the one that we just started. So this is, sort of your basic management console stuff. There is a Firefox. There are different ways to sort of do the same sort of stuff. Command line, folks. There's an excellent set of command line tools that let you grind through all of this. There's this web set from Amazon. There's a Firefox plugin called Elastic Fox. Thank you. RightScale has some tools. So there's different things out there that'll give you the same sort of stuff. If we look at one that's running, we can see the information about it. Let me just pull this up a little bit. There we go. So you can see the name of the instance, the security groups, the status. Here's that zone, US East 1B. Okay. And then a bunch of other information, including the IP address. I'm not using elastic IPs right now. Just
The quick note on the elastic IPs, they're free to get. You can assign yourself an IP address, and you can use it. You can have up to 4 or 5 of them. You can charge $2 a day if you disassociate it from a running instances that are still prominent.
Right, exactly. Yeah, they don't let you sit on IP addresses, which is actually why I had one, and then I cut it loose because I've got plenty of control over my DNS, and it sort of helps then too. So right now we're using we're actually using this to power. I started with the Technoids website. I moved it out to the cloud, so that's actually running out there on the same server as Technoids, just to save a little bit of money. I loaded up this is the DimDim instance. It's powering the conference webcasting. So that's also running out in the cloud on that same instance. And we're in the process of moving the Kali website. This is the Kali website. John doesn't want you to see. It's this is the beta of the new Drupal version of the website, and that's running out in the cloud. So all of our stuff is actually going to end up out there. And now the way that I've got this set up is that in addition to the running instances, we also have the EBS. I've also got EBS volumes. Okay, the 100 gigabyte one is actually where we're storing right now. Where we're storing the data we store both the database and we're storing the lessons out there. And actually, I'm going to move the whole Drupal instance out there because it's volatile enough that I don't want to lose it. But I also back up nightly to a physical server that Dan made me name Skynet. No, because Dan wanted to have a computer that was named Skynet.law.cornell.edu. So he has that.
Robot orbital.
Absolutely. And actually, all it is it's just a really basic server, just packed full of hard drive space. There's 4 terabytes of disk space on it, and we back up everything there. So as I move away from physical servers, I'm actually going to plant one of those like at Emory too with Ben. And we'll probably keep one in Chicago also. And I'll back up to those 3 physical sites just, for the same reasons Dan does, so that he can actually get his hands on something sometime, if he really wants to. Let's swing back over to that image. We should be able to get, so let's see, this is the one we just started up. Okay, now I can, that's it. I can connect to it. It's actually going to give me a little string to run on my terminal on SSH so that I can get into it. And what we'll do is we will pop up iTerm and we will paste that in there. We're going to take away the reference to the certificate. Whoops, because I don't need that. I hope. I think I do. And we should be able to hit.
Oliver, you may want to release your baseball fans.
Oh, yes, I'm sorry.
Go to the lobby.
If the baseball, yes, if there's anybody going to the baseball game, you are indeed released, sorry. I didn't mean to hold anybody up. Oh, sometimes I forget that this isn't really cut and paste, it actually is the command line. Hang on a second. Okay, there we go. And we'll say yes. And that's it. So we just started that Linux server, and now we're in it, and it's running, and that's about all. Okay, I missed that. What did it say?
All your baseball fans are belong to
Yeah,
us.
thank you. No. Poor baseball fans. There's actually a series of buses, anyway. The security groups, just to take a look at those real quick. The security groups give you ideas about, this is how you set, like, what ports are open and stuff on your, at sort of the network level. So, again, you can go in on a given host basis and block these ports and stuff, too, if you want to. Then the neat thing about it, the neat thing and the equally dangerous thing about it is that if you're working on one of these and you're here and you click the terminate button, wait, I'm just double checking to make sure this is the right one.